problem that we are going to discuss is based on conservation of linear momentum as well as angular momentum. In this problem, we have a ball of mass m which is moving with a velocity u in horizontal direction, and it strikes this rod at a distance x from the center of the rod. This is the center of the rod, and after collision, this ball sticks to this rod. The mass of this rod is capital M, and our goal is to determine the angular velocity of the rod when the ball sticks to this rod. Now, the main focus of this entire problem is first the conservation of linear momentum, second is conservation of angular momentum, and these problems are solved in various textbooks, but there are certain doubts regarding the velocity of the ball after sticking and the subsequent motion of the rod after collision, and there are certain doubts that still remains in the students. So my aim is to overcome those doubts. So the conservation laws which are applicable in this problem is conservation of linear momentum, conservation of angular momentum, and we'll discuss a little bit about conservation of kinetic energy. So first consider the situation in which the collision happens. The ball will will exert a force F, which is shown by this green arrow on the rod. Similarly, the rod will exert an equal and opposite force. This is by Newton's third law to the ball. And if we consider this entire as a system, that is ball plus rod as a system, the net force on this system will be F plus minus F, that is 0. So linear momentum of the system, that is ball plus the rod, is conserved. Now considering the angular momentum part, if we consider any point, suppose this is our point A, this is our point A, and we are taking angular momentum of this yellow force, then it is r cross F. This is the position vector r cross F. Similarly, for the green force, which is exerted by the rod on the mass m, is r cross minus F. When we sum these two forces, r cross F and r cross minus F, their resultant will be 0. So in this case, the angular momentum of the system about point A, or in fact about any point, will be conserved. The reason is that our forces are collinear, and they are of same magnitude and in opposite direction. So angular momentum about any point in this entire plane on which this collision is happening is conserved. Now, as far as kinetic energy is concerned, if this ball strikes the rod and sticks to it, so this is perfectly inelastic collision. So in this case, the kinetic energy is not conserved. Now, before going to solve this problem, I would like to discuss a little bit, because this is important for the problem, a little bit about the difference between a point mass and a body having finite dimension. Suppose this is our point mass, it has no dimension. So in this case, there is no rotational motion or angular motion of this point mass. Now consider the finite body. This is assuming it to be a rod of length L, and we are considering about only its translatory motion. So in case of translation, these arrows are representing velocity. These are velocities. So these velocities are equal throughout the length, or in fact throughout the body of any body having finite dimension. If it is in translatory motion, then velocity of each point is same. When we consider rotation, assuming this rod is fixed at point, suppose this is the center of the rod C, and this rod is fixed at this point, so this rod will rotate about this point. In this case, each point assuming this point as A, this as B. Likewise, we can take any point. Each point is in circular motion, and their velocity is omega into r, where omega is the rotational velocity, angular velocity of the rod, and r is the distance from the rod. My objective is to say that in case of finite body, the velocity in case of pure translation at each point would be same. However, in case of rotation or in case of general plane motion, velocity of each point will be different. In case of pure rotation, each point will be in a circular motion, and in case of general plane motion, points will have different velocities at different points. In fact, they do not vary linearly, or they don't show any pattern. They have different velocities, and that can be determined. Now let us take a finite body, assuming this to be a finite body of some dimension, and we take 2 points on it. Suppose this is our point A, and this is point B, and RBA is position vector of point B with respect to A. This is position vector. So to determine the velocity of point B, if we know the velocity of point A, we can calculate VB equals to VA. Suppose, assuming it to be known, VA is assumed to be known, and angular velocity is also known, and this is the position vector of point B with respect to A. So we can calculate VB equals to VA plus omega cross RTA. This equation is valid for any finite body. Now, in general, the plane motion, which we have discussed just now, can be divided into a combination of pure translation of center of mass as well as pure rotation about its center of mass. I will mainly stick to this rod problem, and suppose this is our rod and it is in general plane motion. So in case of general plane motion, and assuming it to be this to be center of the rod, and if it is in pure translation, then each point on this rod will have same velocity, and that will be equal to V. However, if it is general plane motion, each point will have different velocity, and we can differentiate this motion into 2 parts. One is pure translation of the center of mass, assuming the velocity of center of mass as V0, and as well as rotation about center of mass, and angular velocity is assumed to be omega. So in order to determine the velocity of any other point, we are assuming that this V0 is known and omega is known. Suppose this is our point B. So velocity of point B will be VB equals to V0 plus omega cross RBO. RBO is position vector of B with respect to O. That is, this is the position vector of B with respect to O. So if it is in horizontal direction and in XY plane, so we can simply write, we don't have to go for this vector notation, we can simply write VB equals to V0, and after that cross product it will simply be simplified as omega into x. So we need not have to worry about too much about this vector notations. This is simply V0 plus omega into x, omega into x. Similarly, the angular momentum of any point, this is B, of any point B, or you can take it A, B, or whatever it is, can be determined as a sum of angular momentum of the center of mass, which is rotating with angular velocity omega, plus angular momentum of the center of mass about that point. This is the linear momentum of center of mass, m into v0, and this is the position vector of the point about which we are taking the angular momentum. So the angular momentum is of 2 parts. First part is our rotation, pure rotation about center of mass, and second is the angular momentum, assuming the entire mass is situated at the center of mass and the center of mass is moving with velocity v naught, so that will be RBO cross MV naught. RBO is position vector of the point about which we are calculating the angular momentum. I0 is moment of inertia of the body about its center of mass. Now let us consider the situation where the confusion arises. Suppose this is the ball of mass m and it strikes the rod of length L, assuming this to be center of mass or center of the rod. This is point O is the center of the rod. When the ball sticks to the rod and assuming it to be perfectly inelastic collision, what we have studied in for point mass is that when we have one point mass of mass m1 moving with velocity v1 and another one is at rest, suppose this is m2 and it is at rest, m2 is at rest, that is initial velocity is 0. So in this case, when the ball strikes this m1 strikes this m2 and sticks to it, what we say is that they will have both, since it is sticking to that ball, they both will have a common velocity after the collision, and that velocity we assume it to be v. But in this case, when the ball is striking a rod at a distance x from its center of mass. So here in this case, what is happening is what my question or the doubt, or in general the doubt that remains in the student mind is, what will be the velocity v when the ball collides with the rod, whether it will be velocity of this point where they are colliding, suppose I am saying it as A, or point O, I am saying it as point. So the velocity of ball after collision, will it be same as velocity of rod at point A, because rod is a finite body having finite dimensions, so its velocity, and it is in general plane motion, so each point will have different velocity. Point O will have suppose velocity v0, then point A will have velocity va. So the question arises that after collision and when the ball sticks to this rod, whether the velocity of ball after collision is va or v naught or something different. The answer to this problem is that when this ball strikes the rod, after sticking, the velocity of point A of the rod and the velocity of the ball is same as the velocity of point A of the rod after collision. So for example, suppose when we write this equation, the conservation of linear momentum, and this is generally given in our textbook, that mu equals to m plus n into v, then question arises is, what is v? Is it va or is it vo, or is it something else? The answer lies in it that this v is the velocity of the center of mass of the entire system. This is in fact, when we are considering this rod and the ball combined as a system, so it will have suppose this is mass m and this is capital M. Now the center of mass will not be the center of the rod. Center of mass will shift somewhere here. We are denoting it as XC, center of mass of the system. So the system will move with a velocity v, and this is the velocity of the center of mass. neither it is VA, because where it is striking, it is, this point is A. So the ball is having a velocity after collision VA, and which is equal to the velocity of the rod of point A. But in this equation, this is my main focus. When we are writing this equation, mu, this is the linear momentum, because initially the rod was at rest and this ball was moving with velocity u. So linear momentum of the system before collision is mu plus 0, that is mu, and after collision, since it is sticking to the rod, we write capital M plus small m into v. This v is velocity of center of mass of the system, and this is the center of mass of the system, xc, which is at a distance xc from the center of the rod. Now let us analyze one by one. First we consider ball plus rod as a system, and when we are applying conservation of linear momentum, then we are having mu equals to m plus m into v. Here v, again I am repeating, this v is velocity of center of mass of the system. System means rod plus ball as a system. Now if we consider it individually, means generally the questions that are solved in the books are, they consider it this equation, they consider this equation, and they solve it where v is velocity of center of mass. But this can also be solved, and this is my main focus, that ball and rod can be considered individually. So velocity of ball will be equal to the velocity of rod where it sticks with the rod, that is point A, that I have shown in the previous diagram. This is the rod, and here this ball strikes the rod, considering it to be point A, and this is the center of the rod, that is we are taking it as origin O. So after collision, the velocity of ball will be VA, which is the velocity of the rod after collision. Now in order to determine VA, we have to use this equation VA, which we have discussed earlier, that is VA equals to VO plus omega cross RBO. VO is velocity of, this is our velocity VO. VO is velocity of the center of the rod, and if it is known and angular velocity is known, assuming it to be known, if it is unknown we can solve it, then VA equals to VO plus omega cross RBO. RBO is in fact, sorry, this should be RAO. This point is, this is RAO, position vector of A with respect to O. And my again, the point is that we don't have to worry too much about vector notations, because this will simply come out as simple scalar calculation. For example, in this case, VA can be simply written as V0 plus omega into x. This you can verify by the cross product. This comes out to be omega into x. So now this, suppose I am writing it as equation 1. In equation 1 we are using mu equals to m plus m into v. This v is velocity of center of mass of the rod system, sorry, this is v, and it is at a distance xc from the center of mass. xc is the center of mass of the system from the center of the rod. Now writing it as equation number 2, and I am trying to highlight the difference, that when we are considering ball and rod as an individual particle or as individual element, since rod is not a particle, so the equation is mu equals to MVA. This is the linear momentum of the system before impact, because initially the rod was at rest, and this is the linear momentum of the system after impact. After impact, the velocity of ball will be VA, and the velocity of this rod is V naught, which is the velocity of the center of the rod. So we can write it as MVA plus MV naught. Now substituting VA as V naught plus omega into x, this MU equals to MV naught plus M into omega into x. This total is the linear momentum of the ball, and this MV naught is the velocity of linear momentum of the rod. This rod is moving with velocity V naught. V naught is the velocity of the center of the rod. Now first we will solve it by considering, which is generally given in the textbook, considering rod plus ball as a system. This is our ball which is moving with velocity u, and it strikes the rod, and after striking it sticks to the rod. The length of the rod is L, and x is the distance from its center. Center of the rod is O. This is the center of the rod. XC is the position of the center of mass of the system, that is entire ball plus this rod as a system, and XC is the center of mass of the system, and x minus XC is the distance of the center of mass from the point where this ball is striking the rod. Now when we are considering this ball plus rod as a system, we are assuming that V is the velocity of center of mass of the system, which is at a distance XC from the center of the rod. Now when we apply conservation of angular momentum about the center of the rod, then angular momentum of this ball M, which was moving with velocity u, is mux in the direction clockwise. After collision, the ball plus rod system will have a general plane motion. The center of mass of the system will have velocity v, and this rod is assumed to be rotating in we have assumed, because this will be the motion in clockwise direction. This rod is assumed to be rotating in clockwise direction with angular velocity omega. So first, when we apply the conservation of linear momentum, which is generally given in our textbook, this mu equals to capital M plus small m into v. This v is the velocity of the center of mass of this entire system. The entire system is ball plus rod as a system. So this is our first equation, suppose, and when we apply the conservation of angular momentum, so before applying conservation of angular momentum, the angular momentum of the system O after collision can be given as L equals to IC into omega plus RCO cross M plus M into V. Now this first term is the angular momentum of the system, assuming this rod is rotating with angular velocity omega, and this IC is the moment of inertia of the system about the center of mass. Center of mass is C, and RCO is angular. This is the angular momentum of the system, assuming the system is moving with velocity v about point moving with m plus m into, and this RCO is the position vector of point C, that is the center of mass, about the point which we are taking. That means we are taking angular momentum about this point. This is our point about which we are taking the angular momentum, and this is the velocity v with which the center of mass is moving. So angular momentum of this entire system about this point will be first term will be pure rotation, that is IC into omega about center of mass, and the second term is assuming the entire mass is concentrated at the center of mass, that is m plus m is the entire mass, small m plus capital M. V is the velocity with which the center of mass is moving, and RCO is position vector of the center of mass with respect to the point about which we are taking the angular moment. IC is moment of inertia of the system about its center of mass. Now if we take this as origin, then the center of mass, this you can calculate xc equals to uh, m into x, where m is the mass of the rod, x is the distance from the origin, that is x. For the rod, this is origin, so m into 0, because we are taking center of the rod as origin, divided by m plus m. M is the mass of the rod and small m is the mass of the ball. So this term mx by m plus m is the coordinate of the center of mass. Now this ball is moving with velocity u and it sticks. So now coming to the point, that is we have to find IC. So first we will calculate IO, that is moment of inertia of the rod about center of mass, and this equals to ml square by 12. So moment of inertia of the rod about point C will be I0, that is ml square by 12, plus mass into xc square. Xc is the distance, this is xc, position of center of mass with respect to O. Similarly, moment of inertia of ball about point C will be mass of the ball into this distance square, x minus xc square. Now xc we have just calculated is m into x divided by small m into capital M. Similarly, x minus xc can be calculated as we will subtract from it, and this is mx divided by capital M plus m. Therefore, the total moment of inertia of the system about point C, that is IC, equals to I naught plus m into xc square plus m into x minus xc whole square. Substituting the value of xc and x minus xc, we will get IC equals to I naught plus capital M into the values plus small m into the values, and after simplifying we will get IC equals to I naught plus capital M into small m into x square divided by m plus m. Now we have calculated the moment of inertia of the system about point C. Now we are applying the conservation of angular momentum about this point O. So this distance is x. So the linear momentum of the system before collision, because the rod was at rest, is m into u into x. Similarly, linear momentum, angular momentum of the ball before impact was m into u into x. Similarly, angular momentum of the system after collision is m plus m into v into xc, because we are assuming that this entire system is here with total mass of m plus capital M plus IC into omega, where IC is the angular moment of inertia of the system about point C. Now when we substitute the value from conservation of linear momentum, we have calculated that V equals to mu divided by m plus m. When we substitute this value, this equation becomes mux equals to mu xc plus IC into omega. Substituting and rearranging, we get taking this muxc on the left side, this becomes mux minus muxc equals to IC into omega. And when we know the value of x, we know the value of xc, we have just calculated. Xc was small m divided by m plus m, mx divided by m plus m. So we know xc, we can substitute in terms of x, and finally when we substitute these values, we get mu into m plus mx divided by m plus m equals to I naught plus this value. So omega comes out to be this value. Omega equals to, this is our final result which we have calculated. This again I am emphasizing that this we have calculated on the basis of rod plus the ball as a system. Now considering ball and rod individually, because this is not in general not discussed in our textbook. When we apply the conservation of linear momentum, now the question arises is that the linear momentum of the system before impact is m into u, this much we know, and the linear momentum of the system after impact is m in, sorry, this is a mistake, I think this should be mv, if it is point A, then this should be mva. Okay. This is in fact mva. This mva is the linear momentum of the ball after impact plus mv naught, and when we substitute the value of va, which we have found earlier, that is va equals to v naught plus omega into x, so when the values of va are substituted, we get this equation mv naught plus m omega x. This is the linear momentum of the ball after impact, and this is the linear momentum of the rod after impact. Now the linear angular momentum of the ball about point O, about this point, will be mu into x. Similarly, the angular momentum of the ball after collision will be mva into x, because after this is point A and the ball will have the same velocity as that of the rod at point A, so the velocity of this ball will be va after impact. So angular momentum is mva into x, and angular momentum of the rod after collision, because we are taking angular momentum about this point, so this L equals to I naught into omega plus RA, means position vector of A with respect to O, cross MVO. Now since we are taking this point and we are taking angular moment, and the rod is having a velocity V naught at its center of mass, so RA naught A0 will be 0. Position vector of this point 0 with respect to itself is 0. So this term will be 0. In fact, I am cancelling it out. So we will simply have the angular momentum as I naught into omega. Now VA is V naught plus omega x. Sorry, this I have explained you. So when we apply the conservation of linear momentum about the rod center, sorry, this is angular momentum, conservation of angular momentum about the rod center, angular momentum, sorry, then this term is mux equals to mv naught plus omega x into x plus I naught into omega. Now this term is from conservation of linear momentum, that is mu equals to mv naught plus m omega x plus mv naught, and we have simplified it. So we can calculate the value of v naught as m into u minus omega x divided by m plus m, and when this value of v naught is substituted in the angular momentum equation, this becomes mux. This is the linear momentum, angular momentum of the system before collision, and here we have substituted the value of v naught. Here we have substituted the value of v naught. So this is m v naught plus omega into x multiplied by x plus I naught into omega. After rearranging, we get mux minus m square ux. Means this is in fact simply algebra, which you can do it, m plus n. And rearranging the terms, the equation becomes this equation. Finally, we get omega equals to this much. And this is exactly the same which when we have considered this ball and rod as a system, and this here we have derived when we are considering ball and this rod individually.